I'm going to be talking about kind of extending what we were talking about yesterday, introducing you to the idea of doing chemistry in the code, in this case an SPH code. And what I wanted to do was to give you a brief overview of what's been put into CERN that you can play with. Okay, so I've done a little bit of work just to create a small module for CERN that does some of the chemistry and the cooling that I'll be introducing today. It's based on the work that Simon Glover and Mordecai McLeod did in 2007. And it's a very simple model just for looking at H2 formation on dust grains and looking at the H+ chemistry as well. Okay. Yeah, so I'll start with just some basic chemistry concepts, and then we'll try to show you more and more as we go on the lecture how that's been built into CERN and where you can find the various subroutines to play with yourself. Okay. So I'll start with some basic chemistry concepts, which I didn't really go over yesterday. You've seen this idea of a chemical reaction equation. They tend to be expressed in a format which is kind of quite easy to understand. You define a number density of your reactant is defined as the abundance of that reactant times the number density of the gas. Okay. So you may be wondering, well, how do you define a number density if the chemistry is constantly changing? All right? I can't use the number density of H2 if I'm interested in H2 chemistry, because that's what I'm trying to solve for. Okay. Again, you can't use number density of hydrogen because that's also then changing into H2, etc. So what we tend to do when you see this from now on in the series of lectures, when I mention this N here, it's the number density of hydrogen nuclei. Okay. So that's something that doesn't change, okay, unless you are fusing hydrogen together to create something else, okay? So that's fixed throughout time. And that means that in this notation, a gas which is fully molecular in terms of hydrogen will have an abundance of 0.5, okay? Because relative to the number of hydrogen nuclei, you've taken those two hydrogen nuclei and stuck them together into a hydrogen, H2. Does that make sense to anyone? So that makes sense to everybody? Anyone have a problem with that concept? Okay, so that's something I should point out before we start. Okay. I just want to put up some reactions here. Simon normally shows these when he's doing a chemistry talk. I thought it's kind of useful to go over them. Some of them you're probably familiar with more than others. For example, your rate of recombination. You're kind of used to this in terms of your ISM physics. And then you have things like photodissociation. A photon comes in and breaks apart your molecules, but there's a whole bunch of other ones here which also play a very important role in the ISM. Again, you're used to seeing photoionization, etc., from looking at ionization regions. Okay, so we're not going to be looking at all of these today. In fact, the model that I've got doesn't, that I'm showing today doesn't really have very many of these, but it's useful to see them because if you want to extend your model, then you will have to look at these different reactions, and it's sometimes good to know what to call it. Okay, so when you're looking for a particular reaction, what is that reaction called? It's called a charge transfer reaction. Okay, so you can go and look it up. I should also say that we should kind of define our abundances to begin with. These are the solar abundances that we're using in the module, and they're defined in a parameter file, which I'll come on to later. Obviously, the helium abundance is not going to change because that doesn't, that's just set by the Big Bang, and then it's changing a little bit from star formation as the universe progresses. But that tends to be roughly the same. However, these other elements might change, the abundances might change if you were to look at, for example, a low metallicity system. If you wanted to study the chemistry and cooling in Large Magellanic Cloud, for example, you then have to drop these abundances down. And the simple way to do it is just to scale them down by relative to these ratios. These are the solar abundance ratios, okay? So if I was to look at a gas which was 0.1 solar, I would just multiply each of these things by 0.1, okay? And typically, you'd also have to then reduce your dust amount as well in the calculation by the same factor if you wanted to keep the gas to dust ratio scaled down from the solar abundance value. Okay. I should say before we start, the gas to dust ratio that's in the code at the moment is assuming 0.01. Okay. So it's a hundredth of your total mass is in dust. Okay. Okay. So how do you do the reaction rate? So they normally have this kind of very kind of obvious form. You have the total amount, the reaction of creating this kind of molecule AB is given by some reaction coefficient, normally given the symbol K, times the number densities of A and number density of B. Okay, so that's what it would be if you had a two-body reaction. If you had a three-body reaction, for example, let's say a three-body H2 formation could have 3 hydrogens involved, then you would just replace this with N of H this time for hydrogens cubed. Okay, and so what you have to be careful of is that the units of this reaction coefficient can change depending on the reaction that you're looking at. Okay, in this case, the units are going to be will be centimeters cubed per second, because you're multiplying by 2 times centimeters cubed, 2 times per centimeter cubed here, and you want the reaction rate to be in centimeters cubed per second. Okay, because you're looking at the number density of the final species. Okay. A way to think about the reaction rate is simply as some sort of cross-section involved with the collision partner and then the velocity here. Okay, so the velocity of where is the relative velocity of A and B, and you're averaging over the velocity distribution. So that's basically what's going on there. If you imagine you did your stellar dynamics course and you're looking at the collisions, you propagate this kind of cylinder in space and you look at the number of collisions you have. That's essentially what you're doing in the reaction rates, but there's a huge amount of potentially quantum mechanical physics that's getting buried inside here. Okay, and physical chemists have went away and done all that hard work for you. So you're taking the reaction rates that they've developed maybe over years sometimes in their calculations.
So we were talking about how units of K could change depending on that reaction. So that formula for K would also have to change with the three body.
Potentially, yeah. Yeah, but yeah, I mean, so the formula would be very different. I mean, the three-body reactions are kind of counterintuitive one anyway, because it doesn't just involve this cone in space. You have to worry about intersecting trajectories, so it's very complicated, right? So, but all that comes out in the wash, and at the end of the day, that reaction rate is then just done in terms of, it has to give you, this side of it has to give you per cube, the number density per second of the new species, okay? Okay. So yeah, just be careful when you're looking through the literature, you'll notice that does change quite a lot. So another way of thinking about it is that you have a collisional cross-section and a reaction probability that's going to combine together. And the size of that cross-section is going to depend on the type of the interactions. Okay, so if you imagine you had no long-range force, say you had two neutral objects coming together and they're banging together, you could almost approximate them as solid spheres, and that is indeed often what the chemical reaction rates are doing. If you have some sort of charge, then you've got a long-range force, then you have to worry about the Coulomb potentials as well, and that's going to change things that way as well. Okay, so just to note that this hard sphere approximation can sometimes work if you want to get a quick estimate. If you are involving charges, it's not going to work so well, and you have to look at a more quantum mechanical method. In the case that you are independent of velocity, then you just have this reaction rate goes to the temperature, and then the mu over here is then given by the mean weight. So the what do you call it? The if you have two binaries, you have the reduced mass of the system. So it's the same thing you're going to have over here. If you do have a long-range force, then obviously it's going to depend very much on the velocities of the system. Then you're going to be more like a kind of Bondi Hall kind of situation where you're looking at Bondi Hall accretion in a gravitational system, and then you are going to have a much stronger dependence on the velocity, and that actually gives you t to the minus a half on the bottom. Okay, so the form of that reaction coefficient can change very dramatically depending on the system you're looking at. But again, for most of the purposes you're looking at, all that hard work's been done for you, and all you're really doing is taking that one number, the reaction rate, and then using it. Now you might find that the reaction rate itself is a function of temperature and density, as you see here, and so you then have a functional form. And as I was saying yesterday, if you're using a more complicated system of solving the chemical reaction equations, not using backwards differencing, using something like one of these higher order, second order backwards differencing, or implicit Runge-Kutta, you then have to worry about the functional forms of these reaction rates not being continuous, okay, over your temperature and density space. Okay, so that's something to look out for. So once you've formed your molecules, in this case, let's say H2, you can then destroy them again. You can destroy them via chemical processes, which involve more reaction rates over the ones we've just seen. Okay, so there'll be a reaction rate for the destruction as well. Or you have another process just called photon dissociation, where you have your molecule, it encounters a photon, and then it breaks it apart. And what's important to realize is that different chemical species photodissociate in different ways. For example, H2 has very narrow absorption lines. What that means is that when the photons are coming in, they're actually better absorbed by other H2 molecules. Okay, so H2 can then self-shield very well. So if you have a very large cloud of H2, the H2 forming and being destroyed at the surface is preventing the stuff from being dissociated in the center. Okay, so you have to worry about the column density of H2 that you have, and that's therefore not as a kind of long-range effect. You have to worry about the chemistry that's going on somewhere else in your box, and it can be quite difficult to calculate the self-shielding as a result. In contrast, CO has very broad absorption lines, and so it's actually better shielded by dust, which then has this whole continuum of absorption. And also the fact is that CO also is made from carbon and oxygen. We've just seen, if we go back to that kind of slide at the beginning there, the abundances of carbon and oxygen are 10 to the minus 4 of what they are for example, hydrogen. Okay, so you've also got much less of it. So it's not able to self-shield as well. Okay, so CO depends on the total amount of column that you have in dust in your system. Okay, now, okay, that's a long-range thing again, but you don't have to worry about the chemistry there. That's just a total column that you have in your simulation. So in some ways, it's an easier thing to estimate the shielding from CO than it is to estimate the self-shielding. Okay, you don't have to worry about faraway chemistry somewhere else in your box. So how does H2 form? Okay, so we're going to go through a few different ways in which you can form the H2 molecule, and then eventually we'll come to the one which actually dominates in the ISM. Some of you may know that already. The most obvious one is to say, well, why can't you just bang two hydrogen atoms together and form an H2 molecule? It would seem to make more sense. That reaction is called a radiative association, just so you know, so if you have to look it up at some point. You'll find out a radiative association is when you have two atoms coming together over here, or two species, you end up with some sort of a reactant forming, and then you end up with a photon being emitted at the other side. So why doesn't it work? Well, the problem is that when these two hydrogen atoms come together, they have excess energy, and you have to get rid of that excess energy. Okay, and what's happening is you're forming for a very brief time. You might form an H2 if the collision cross sections are correct and they encounter each other. You form an H2, and then the problem is then to emit that photon that's going to carry away the excess energy, you have to do some transition. Okay, so it depends on the Einstein coefficient of the energy that's going to be excited by the excess kinetic energy. Okay. So you have to wait for that photon to be emitted from the from the thing you've just created. And in the case of H2, the Einstein A coefficient, is such that it's a very, very long and it's a very, very low probability of that photon being emitted right at the point where you've just formed it. Okay, so the chances of it occurring are very, very small. If you were to create it's actually exacerbated by the fact that H2 has no dipole. If there were two different weights of atoms coming together, then you would have a dipole transition, and they have much smaller Einstein coefficients. Okay, so you get much more likely to create a photon in that time, and then make that thing stick. So H2 has a problem in the fact that it is symmetric. Okay, and if you were to actually go through the maths and look at typical ISM densities, you're looking at the age of the universe just to turn 50% of the gas into H2. Okay, so clearly that can't dominate in the ISM. There has to be something else happening. The next most promising is the ion-neutron reactions, and when I come back to my lecture on Thursday, we'll be talking about population 3-star formation. This actually plays a very important role. And what you're doing here is you have a neutral object, you have then some sort of ion. In this case, it's either electron or a proton. And that can excite inside. When these two things come together, they can repel each other, and you create a kind of small dipole briefly, and you can have some transition. Okay, and then it increases the probability that this will stick. Okay, so then you create this H minus, and this H minus does the same thing again. Okay, and then you can finally form your H2. And then what you find at the end is that the electrons and the protons are then left over. Okay, so they are catalysts for this reaction. And that's important. We'll come back to that on Thursday again, because then it means that the number density of these guys and how they're evolving in your gas then strongly influences how much H2 you can form by this process. The problem is that the both chains are initiated by this radiative association. reaction. So similar to what we had before, it is, now we've seen before that it is slow. You have to wait for this photon to be emitted, okay? So you're waiting for that chance to get rid of the energy during that very, very small time that these two objects come together, okay? So it isn't as efficient, but it is more efficient in this case because you have something resembling a dipole when they're forming. However, the other problem is that these H- and H2 plus species are extremely fragile and they can be knocked apart by the interstellar radiation field. The photons that are there can easily break apart these. And so you destroy half your reaction chain before it's had a chance to do anything. Okay. So in the present day universe, this reaction chain might do something, but it's doing very, very little compared to what it would do in the early universe. We don't have a strong radiation field. So for first stars, for example, the population of 3 stars, there is no interstellar radiation field because there are no stars yet, right, for the very first ones. And so this process can actually take place quite well. And also the gas hangs around in a cosmological mini-halo for a long time. And so it's got time for these associated radiative association reactions to take place. Okay. So again, it's not going to be very useful for us here. A third option is to bang 3 objects together. So this is a bit like binary formation, if you want to think. It's a bit like trying to form a binary out of 3 objects. Okay, so you can't form a binary directly from 2 objects because if either they're bound to start with, in which case they're already in a binary when they start. But so without any dissipation, you can't create a different system. Okay. So the analogy here is that you need a third body to take away that excess energy to create a smaller system. In this case, we're trying to create an H2. And you can do that either by using another, you can use hydrogen. In this case, you've got, in this case, you're reacting 3 hydrogens together. 1 takes away the excess energy. Or you're using a pre-existing H2 if you've already got it, and then using 2 more hydrogen. And using this H2 then is this time taking away the extra energy from the system. Now, the problem is that to get those 3 bodies to interact all at the one time requires quite high densities and quite high temperatures. The temperatures you need are around about 1,000 Kelvin. The densities you need are around about 10 to the 8 number densities. Okay, so that's quite high. So it's not going to work in the ISM, and it drops off like a stone when you get to lower densities and temperatures. So it's not going to be particularly important in present-day star formation. Again, it plays a very important role in primordial chemistry, and I'll come back to that later. Okay. So how does H2 actually form in the ISM? Well, it forms in dust grains. So basically, the dust this time is playing the role of the third body. Okay, so what happens is one hydrogen atom comes onto a dust grain, sits there. Eventually, another hydrogen atom will come on and hit the dust grain. The dust grains are big, remember, so it's quite easy to find them. And then once they're on the dust grain, they can bounce around and they can find each other. They form an H2, and at some point they'll pop off. Okay, and the reason they pop off is that you have to put a little bit of energy into that system, take it from the dust. It pops off and it launches itself away from the dust grain. It does depend quite strongly on the dust temperature. If the dust is hot, then the H atoms have problems sticking to the dust grains. So there's this functional form here. The temperature here is just the temperature of the collisions. Okay, so that's how often the H finds the dust grains. This one here is the one that really says, well, how hot is that gas compared to the dust grain, and does it stick to the dust and stay on the dust? Okay, does it get pushed off? And then you have the number density of the gas here and the number density of H. The number density here is actually to work out the number density of dust grains, which has been convolved into this coefficient of the fun here. Okay, so if you wanted to change the gas to dust ratio, you'd have to multiply this by a different number. Okay, this number here is set for solar gas to dust ratio, which is around about 0.01. Okay. Okay, and then you have the number density of the collider. That's fine. So if you plug some numbers into this equation, if you take a kind of a temperature around about 100 Kelvin, which is kind of typical of the cold neutral medium, maybe in the kind of the regions around in the kind of warmer H1 envelopes around the GMC, for example, you find that the reaction rate goes as 10 to the 9 over the number density. Okay. So if you had 100 Kelvin, gas and you've got maybe a number density of a few hundred, then you're looking at tens of mega years, which is getting quite good. However, what Simon was showing in his calculations that he did with Mordecai was if you have turbulence in the ISM, you're constantly pushing gas to higher densities. Okay, and also you're pushing it to higher densities, and also the temperature of the gas is going down slightly as well. So it makes the sticking parameter more efficient. And then this can actually become mega years eventually, right? You're pushing stuff up to mega years. Cool. So that is the most promising way of forming H2 in the universe. Now, people have said that, have always claimed that because of this formula, they've always claimed that, well, GMCs must take a long time to form. They must take tens of megayears to form, because they're always thinking of something which is a big static cloud gradually sitting and collapsing. And I'll show you at the end, actually, that's actually not true. Some work that Claire Dobbs did. And Simon's results were showing that, well, that turbulence just does help you play around with this number density here, and you keep pushing gas up and you keep it converting. And once you've got the H2 there, it takes a while to dissociate it because it self-shields, as we were talking about before, okay? So once it's there, it's more difficult to get rid of it.
So when you write just N without the subscript, that's the dust density?
The whole system is dependent on N here because, so this N is a proxy for the dust. Yeah, it could have been the dust density that was put in here. What's actually done is you actually put in the dust density of the gas, and then you're assuming a gas to dust ratio. Okay, so so this would, if it was to be written in terms of the dust density, this would be 10 to the minus 16 at the front, and then the dust tends to be 100 times less dense than the gas because it's only 100th of it by mass.
So what's the difference between N and H?
And H in this case is the number density of the hydrogens.
And N includes other gases?
N includes, that's the number density of, that's what I was talking about before. Every time you see N here, it's a number density of hydrogen nuclei. Okay, so that's everything. So you can't make, you can't create and destroy that in the code, right? That's always fixed. The problem with number densities is they depend on mean molecular weights, right? The number density of hydrogen nuclei doesn't depend on mean molecular weight anymore. Unless you're fusing hydrogen together to create new things, you're not going to lose it. It's just been locked up in various different processes, but it's all still there. Does that make sense?
But it's still not accounting for like the helium?
It does take, yeah, we do actually take the consideration of the helium in there as well. And the helium is not changing throughout the system either. Yes?
The first reaction, the HS, what's the rest of
What, sorry?
HS, the first reaction?
That's just saying that this hydrogen is sitting on the dust grain surface. Sorry. So yes, the hydrogen that's on the surface of the dust grain. Any more questions before we go on? Good. Okay. So what Simon did was he took, in 2007, he put together a very simple series of reactions. I mean, he had to do quite a bit of work to figure out which ones were the most important. So he created a reduced reaction network. Remember we were talking yesterday, you want to always keep the number of reactions as small as possible and the number of species that you have, because the more you have, the more difficult it gets to solve it computationally. So what he did was he was able to reduce the number of reactions to 8, and I'll show them in a minute, for forming H2 and H+. And a part of the reason why he was tracking the H+ is that in the warm neutral medium, recombination cooling is very important. Okay, so you have an electron and a proton. The cooling, you get a cooling process from putting the two of them together. Okay, so he wanted to be able to look at H2 formation in the warm neutral medium all the way down to the cold neutral medium. So that's why he was also following the H+ here, but not just following the H2. So the H2 that he's following is the formation in dust grains, and I'll come and show you that in a minute. And what I've done is I've kind of packaged together Simon's reactions that he used in that paper, based on our more complicated reactions that we use for our standard ISM model. So I've kind of ripped them out of Simon's normal chemistry and put them in a kind of more Fortran 90 friendly little package, which sits in a subdirectory in CERN, which I'll show you later as well. Okay, and it's basically the code that I've developed is just a one-zone model. Okay, so your SPH particle comes along and says, I have a temperature, and I have an energy, and I have an abundance. And then it goes into the subroutine, and then it figures out the new temperature and the new abundance, and comes back out again. Okay, over a time step dt. And you can also take that out if you wish and play with it on its own. You don't need to have it inside the whole SPH code. People do things called one-zone models, and they're very useful for trying to figure out roughly which chemistry is important where. And in fact, Mark has a code written called Despotic, which is on his website somewhere, which is a much more complicated version. It has many reactions and has very many heating and cooling processes, but it's essentially a one-zone code as well. Okay, so you can go to Mark's website and play with that. Okay, and like I said, they're very useful for trying to work out what would the equilibrium temperature of a parcel of gas be that had a density of, say, I don't know, 100, and it was sitting in a radiation field which was like 5 times the local interstellar radiation field. Okay, you can go away and figure out what the equilibrium abundances would be. You can go away and figure out what the local ionization fraction would be, etc. Okay, so you can rip this out if you wish to and play with it separately. It's sometimes a good way of testing the code is to take it out of the SPH simulation and play with it on your own first. That's what I did before I put it in here. That's what Simon did before he put it into Zeus when he was doing this paper in 2007. So which reactions do we have? So the first one, the top one there, is the one we're talking about there, with the two hydrogen atoms coming onto the dust grain and forming H2. Obviously the grain is still left, hasn't been destroyed in the process. So you can think of the grain as a catalyst here, if you want to think about it technically. And if you want to see some further reading of where that comes from, it comes all the way back from Heidelberg and McKee when I was born, in fact, in the year I was born. So it's been around a while. It hasn't really changed very much, which is good. The other process he has destruction of H2 by collisional dissociation with either hydrogen or by H2. Okay, and I've only included here the low density contributions. There are different reaction rates at high densities. So if you wanted to do the full problem, you have to splice the reaction rates from the high densities to the low densities, and there are ways to do this in literature. In fact, Simon does that in this paper. I didn't do it here because the high density collisional dissociation is only important when you're getting into the way down in a prestellar core when the star's about to form. That's its last coolant, basically, is ripping apart hydrogen. You probably know this from your star formation lectures. You have this. So first of all, your dust goes optically thick. You form that hydrostatic core. It gradually heats up and heats up, heats up, and eventually it starts to break hydrogen, molecular hydrogen apart, and it behaves like a coolant, and it can behave almost isothermally from there. That is the dissociation that occurs at high densities, which I've not included. Okay, so all I've got here is the low density stuff. And again, you can go and find these reaction rates in literature. The next one, the last one is this one I was talking about before, how you can break apart the H2 from the interstellar radiation field, and you just go back to having hydrogen again. Again, the rates here are from Drain and Bertoldi in 1996. I'll say a little bit more about that in a minute. The H plus chemistry is the next 4 reactions. The quickest way to make it, the most dominant way of making H plus is by ionization from cosmic rays. So the cosmic ray comes in and batters the thing, it pops off an electron, it actually does a whole slew of chaos that happens after that, which actually isn't taken into consideration here. But that's going to create the most of your H plus. You can then have recombination, and you're going to have collisional ionization with electrons, free electrons that maybe have been liberated by the photoelectric emission, for example, and they can also ionize your gas. And then you can recombine. You can recombine in 2 ways. You can do it in the gas phase. So you just have your electron and your proton recombine. That's normal recombination you're used to seeing when you're doing your Stromgren sphere calculations. And they can also recombine on the dust grains as well. Okay, in this case, either the electron or the H can be sitting on the dust grain. It finds another one, and then again, they can find each other, and you pop off a neutral hydrogen. So in that. We've talked about hydrogen and we talked about H plus. So you can see you've got H2 and H plus, and those are the species that we're going to be following in the code, right? But what about the neutral hydrogen? What about the electrons? What are we doing about them? Well, they're actually quite easy to follow because they are just come from pure conservation equations, right? The total amount of hydrogen I have is just a function of the amount of H2 that I formed and the H plus, because that's all the hydrogen I have in my reaction network. Okay, so it's trivial to calculate the abundance of neutral hydrogen at any point. And the same goes to electrons. Electrons are a little bit more complicated. They can come from H plus, but they can also come from actually C plus and from silicon. And the reason why we've written just in terms of carbon here is that we're assuming in this simple model that all the carbon is in the form of C plus. Okay, so in principle that should be C plus here, but in practice it's just going to be the neutral carbon, right? Because we're not actually following the carbon chemistry to push it from C plus into neutral carbon and then maybe into CO or HCO plus or something. Okay. And so again, the silicon is also going to be ionized as well. Okay. Now you can also make some better approximations. Some of the approximations for CO that I'll be showing you tomorrow actually have an extra term. They have a metal term, which goes over here. So other metals, which are higher, more massive objects, can also contribute electrons as well. And so that would then change. And remember that from this definition here, remember the reason why there's 2 here is because we've defined that the abundance of hydrogen when it's fully molecular, or of H2 when it's fully molecular, is 0.5. Okay, just so you know. Okay, so those reactions are endothermic and exothermic. Okay, there is heating and cooling going on inside the code while those chemical reactions are taking place. Well, also in reality. So which ones are heating and which ones are cooling? Well, the heating ones are shown here in red. What people don't tend to think about is that H2 formation actually heats the gas. People always think, oh, H2 makes gas cold, which is nonsense, right? H2 doesn't really cool in a GMC, doesn't do anything at all. And actually forming H2 can potentially heat the gas, okay? Because you have this barrier in the H2 which you have to overcome, this 4.4 eV, and then that releases heat into the system when you form the H2. Now, what we're assuming in this very simple model is that some fraction of that heat goes into the H2 as it pops off the dust grain, so it goes into kinetic energy of the H2. And the other fraction of it goes onto the dust grain and then is immediately radiated away. Okay, we don't follow this. We don't track how much it's heating the dust grain. We assume the dust grain has a big enough reservoir that it can deal with that and just radiate the heating term. In reality, also another fraction of it goes into exciting the H2's electrons inside the molecule. And then what can happen then is that H2 can pop off and then collisionally de-excite somewhere else and then pass the energy on. Again, we're not going to do that. It could also spontaneously decay and then just emit a photon and also go away. Okay, so we're not including that extra term, which is much more complicated and also, I should say, horribly, horribly uncertain. If you look in literature and look at people trying to work out the various fractions of those 3 things I've just told you, they will vary wildly. Okay, so we're just going to pick some number in this and stick with it. The other heating mechanisms are, so I've just said that creating H2 heats the gas. Breaking it also heats the gas if you're breaking it from something that came from outside the system. Okay, so if you have a photon, which is coming out, that's a photon coming from the interstellar radiation field, which is not inside your system. It's pushed its way through, eventually breaks the H2 molecule. You then take energy from outside the system and put it into the system, so that also heats the gas. Okay, so if you have a region where you're constantly forming and destroying H2, that's getting hotter and hotter and hotter. Okay, something I think people don't tend to appreciate so much. The other thing which heats the gas is the cosmic ray ionization. You're popping that electron off. That electron has got lots of energy, and that's increasing your basic thermal kinetic energy. Okay, the rest of them are coolants in some way. So if you collide to, if you collisionally dissociate your H2, you also cool the gas. You've taken the energy that was in the system and you've broken apart a molecule. Okay, so you've ripped some energy out there. So that's the cooling that you get, like I was saying, in star formation, where you're dissociating hydrogen, molecular hydrogen, to try and stave off the isothermal during the collapse. You also have recombination. You also have collisional ionization cooling with electrons here, and then you also get recombination cooling. But only if this photon escapes the system, right? So we've got that photon coming away, right? So if that photon manages to escape the cloud, you've cooled the cloud down by recombining and emitting that photon. Okay. Okay, so there's a lot going on there, and some of these are important, and some of them aren't, and it depends on the regime you're in. Okay, so you have to be careful. What's the biggest heat source in a cloud? It's actually the photoelectric emission from dust grains. People always used to think that GMCs, for example, were heated primarily through compressional heating and shocks. That's not true by orders of magnitude. Okay, orders of magnitude is coming from photoelectric emission. So what photoelectric emission is UV photons coming into a dust grain and knocking an electron off. And those electrons then contribute to the thermal energy of the gas. Okay, that process keeps happening. The gas keeps getting hotter and hotter and hotter. The rate that we're using in this system is from Bakes and Thiele's. There's been a small addition from Wolfire, which takes into consideration these PAH complexes, which are often coupled into the dust, general mess of dust. We call it dust, but it's not. It's actually some molecules and also dust grains. So there's been a slight modification there. And it depends on the strength of the radiation field. That's chi effective. depends on the extinction, how far in the cloud you are, and the original radiation field. That's given by this chi parameter here. It's normally expressed in units of the Habing field. For those of you who are used to seeing that, that's the strength of the radiation field at 1,000 microns, okay, 1,000 angstroms, sorry. And there's also this epsilon parameter, and the epsilon parameter basically is the efficiency of the heating, and it's actually a function of, again, chi in some way, because it takes into consideration the strength of the radiation field and also the electron fraction of the gas. And the reason why is that the electrons are much easier. The electrons can remove themselves from the dust grain much easier if the dust grain is either neutral or it's slightly negatively charged. Okay, if this dust grain is positively charged, then it has to fight against the Coulomb potential as it's escaping the dust, right? And so it can't escape quite as easily, and it generally finds itself smacked back on again. Okay, so the more electrons you have in your gas, the more, generally because of collisions with the dust grains, the more neutral or negatively charged the dust grains are going to be, and so this process is actually more efficient. Okay, so it's kind of somewhat counterintuitive that the efficiency depends on the number of electrons you've got in the gas when it's electrons you're trying to get out. Okay, so there is some kind of sweet spot there. And if you look in Bakes and Thielens, you can see a nice figure which shows this much better than I've described it. Okay, so. But again, you've got to see this as a problem. You need to know roughly what the strength of the radiation field is at your point in the simulation box. Okay, so that's going to be an issue. So how do you treat the shielding? So the photoelectric emission depends on where you are in the clouds, and also your chemical reaction rates depend on where you are in the cloud. Okay, so the more photons that can break apart your molecules, the less of that molecule you're obviously going to form. And so you need to have some idea, some estimate of how many of those photons you have passing through your cell at any time. As I said before, if you're looking at H2, it's more complicated because it's not just dependent on the total column of your cloud, it's also dependent on the column of H2 all the way out, because the self-shielding is very, very important. Okay, so that's very tricky. So how do we estimate it? So in the code you're going to be using, it's estimated extremely simply and very, very badly, and something you could do while you were here is then try and come up with a better way of doing this. Okay, so I've just stuck in something very simple. I'm saying the total column density is given by the local number density of the particular cell times a length scale. And I'm fixing that length scale at the moment. Okay, so if you're looking at a GMC, let's say 6 parsecs, 10 parsecs, and you can play with it and you can see the effect that it has on your chemistry in the end. So if you're looking for the, if you need to know the number density of the column density of H2, for example, you would then just take the number density of H2 locally and then multiply it by that length scale. Again, you're then assuming that you've got the same H2 fraction everywhere in the clouds. That's probably wrong. Or if you're looking for the total column of the cloud, if you're looking for the photoelectric emission or for the CO shielding, then it's just going to depend on the general number density of the cloud. Or for example, if you're looking for the column of dust, then you'd have to multiply that by the gas to dust fraction again, as you were saying before. And then you're multiplying it by that length scale. So in practice, how you choose that length scale is going to make a huge difference to what you get out. Okay, and that's been a very, very complicated problem so far. So tomorrow, what I'll actually do is I'll show you how we do it in our code. So we developed a new way of doing this, which you're free to distribute. It's a wee bit tricky to implement in the code. It involves hacking the gravitational tree. But again, you're free to do it. Another way of doing it is just by interpolating your particles to a grid if they're not on a grid already, or if you're using a grid code, just using the grid and then firing along your axis to try and get some estimate of the actual columns. Okay, but again, you can do that if you wish. I will help you implement that this week if you wish to. But I'll speak more about it tomorrow. Any questions on that? Okay. So we said a bit about chemical heating and cooling, and we also mentioned a bit about the heating by photoelectric emission. How does the gas cool in the ISM? Well, upwards of around about 8,000 Kelvin or so, the cooling is dominated by atomic resonance lines. Okay, so those, and you're probably most familiar with, Lyman alpha cooling, which is the electronic transitions, within the atomic hydrogen. But there are other ones as well. For example, helium plus, helium 2 plus can also cool the gas as well. Okay, so various transitions within there. You can get a lot of this just by using a tabulated cooling rate which is available from Sullivan and Dopita 93. They kind of combined all these processes together, and you can use it just a simple tabulated function. What I've done here is not quite do that. I want you to see how it works, so I've actually taken just the Lyman alpha cooling and done that on its own. Okay, so there's a line just for Lyman alpha. That's all we're going to be including in that regime at the moment. Okay, and it is the most dominant one. When you're 8,000 Kelvin, as you go to higher temperatures, then it's not quite so effective. The cooling occurs primarily through carbon plus, or C1, and neutral oxygen. These are fine structure transmissions. They're forbidden emission lines, and they cool the gas very, very well. In the regime between round about, well, basically from 8,000 Kelvin downwards, they tend to dominate. And typically, people find that the oxygen cooling and the carbon plus cooling are around about equal. So what I've done in this very simple model is I've only included the carbon plus cooling. If you want to put the oxygen cooling in, again, you can. But for the moment, only carbon plus is in there, and that will give you approximately the correct answer within a factor of 2, okay, or probably even better. Okay. So for just now, that's probably fine. Given the uncertainties and everything else, that's probably okay. And when you get to very high densities, so that will take you down to carbon plus cooling will really get you down to around about 20 Kelvin. Okay. You can get very, 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 very cool. In practice, you would actually have CO forming at some point, and then you cool by CO. We're not including carbon monoxide in the reaction network here. It's just the H2. Okay. So again, I'll be talking tomorrow about how you could include CO if you wish to do it in some simple way, and then you could include the CO to be self-consistent. Okay. I'm over time. Okay. So at very high densities, at 10 to the 5 or so, you're then thermally coupling to the gas. You're thermally coupling to the dust grains, and it's collisions between the. So basically, the molecules come along, they hit the dust grain, they heat the dust grain up, removes the energy from the molecule, and then the dust grain just radiates away that energy. Okay, and the rate that we're using is the one from Heidelberg and McKee, which is given here. You can go and look it up. Okay, or you can actually look inside the code and see how it's done. Okay. So just a quick overview of all the heating and cooling processes. This is a confusogram. You might want to go away and look at it in your own time. You're probably not going to be able to get much out of here for just now. I just wanted to show you that the photoelectric emission, which is this red line here, really is the dominant heating rate. And then in this cloud, which had number density around about a few hundred to begin with and started off atomic, at low densities, you see the carbon plus is this dotted dash line here. You see it matches the photoelectric emission. And at some point in this particular reaction network, we have CO forming, and then it starts to take over. And then eventually, this green line is when you thermally couple to the dust. Okay, so you can see the different processes that are important at different regimes within the cloud. Okay, so if you want to go away and figure out what's going to be important, you might want to look at that plot first and then see if it's worthwhile putting it in. Okay. So how do we do this in the code? How long do I have, actually, by the way? I only have 5 minutes. Didn't we start at like 15:15? Huh?
Oh.
We started quarter. We started. Okay. So I get 15 minutes.
Yeah.
Okay. Well, thank you. That's good news. Okay. So the equations. So you'll notice that. So you recognise these equations from yesterday. This was our backwards difference formula, written now in terms of the two reactions that we're going to solve. We're going to solve for the H2 and the H+. I remember again we mentioned that the form of this equation is such that it can never go negative, which is good, right? It's always going to be positive, because these are defined to be positive, and they've just been the way it's been rearranged. It comes out in this fractional form here, which is nice. The energy equation, you're going to go in with some energy E naught, and then you're going to be evolving over time dt. There's going to be chemical heating and cooling. So gamma is heating in this notation, and the cooling is given by the lambda. You're going to have chemical heating, ISM heating, and then there's going to be chemical cooling, ISM cooling, and then you're going to be multiplying that by time step dt. However, now you have two options of how to solve the energy equation. One is that you operator split, and you do your PDV and shocks and everything in the hydro, and then you store that as a heating term. You think, okay, that's fine. Okay, I keep that to the end. And then you solve the chemistry separately, in which case you have that same equation as I just showed there. A better way to do it, and one which is actually much more numerically stable, is to pull in the heating and cooling from the code itself, the compressional heating and the shocks, and solve it with the chemical reactions, heating and cooling. Okay, you'll get a much, much better solution here, and it's much more numerically stable. And I'll show you on Thursday situations when this can go horribly, horribly wrong. Okay, people have made a lot of deal out of something which is just numerical noise. Okay, so in the version I've got just now, this is what I'm doing. I'm actually passing everything in, and so it's been solved self-consistently inside. Okay. How do we solve the equation? So, the problem with implicit equations, obviously, you have T1, the thing you're trying to get to, on both sides of the equation. So you have to make some sort of guess the first time, and then you have to iterate around. And the simplest way to do that is via Jacobi iteration. It's very dumb. You basically come in and you say, you compute, for example, the reaction rates we just had there. You compute H2 abundance using the values at T0. So you work out your creation destruction terms based on the current state of the gas. You then compute, you do the same thing for the H+. Then you work out the energy. Then you update your electron fractions and your H fractions based on the abundances that you've just that you had from the first step, also at T0. And then you go around again. Okay, you just keep doing that until eventually you get to some sort of solution which you think is acceptable. So you have some tolerance, and you say, okay, I'm done, I'm fine. And you go around, and you keep going around this loop. Okay, so that's Jacobi iteration. Much better and much faster is Gauss-Seidel iteration, which is a very simple step. All you're basically doing is, as soon as something is available, I'm using it again. Okay. So what you do is you go at to get to the T1 abundance of the H2, you use the values that you come in with again, same as we did before. Now what we do is now we update the hydrogen and electron abundances before we do anything else. Okay, so we've just done the H2 equation, we update the H and electron. Now we go into the H plus using these new kind of half-step updated abundances, and we get the new H plus. Again, we update the hydrogen and electrons because they're going to come into the energy equation, because remember the photoelectric emission is going to depend on the electron abundance. Then we update the energy using these new values. Then we update T. Then we go back around again. So basically, as soon as something becomes available, you use it in that iteration step, and you keep going around, and it's much, much faster. It should get to a solution much quicker. Okay, so that's what we're doing here. Now there are ways that solve can fail. One way is that the abundances may fail to converge. They also may change too rapidly over the time step. You might want to constrain them so they're not changing too rapidly, just as, that's sometimes a good idea if you're using a first order backwards difference, because you don't really have a handle on the error there, right? So you're trying to be careful. And they may change by more than a pre-allowed amount. Okay, so you may have decided I don't want at any particular time step my abundance to change by a certain factor. Okay, so that could be a problem. The other thing is the energy might change too much over a time step. You might not want to change by say a tenth or so, any more than a tenth, which is what we're doing here. And more importantly, the energy may go negative, right? Because although I've said that this equation is guaranteed to be positive, unfortunately there's no equivalent way to write the energy equation. Okay, it can go negative if that time step is too big and the cooling was too large. Okay. So the energy can go negative, and that's obviously a pain. So the best way of solving this problem is to reduce your time step and go back around again and try to iterate again. Normally you find that it does converge the second time around or so, right? Now the problem was that the SPH code wanted you to go over a certain time step which had already set, because that's a time step at which the integration scheme is evolving. And so you then have to subcycle. Okay, so that chemistry and cooling has to subcycle within the step until it gets to where the SPH code wants it to be. Okay. And so you have to keep calling the solver until you got to where you want. Okay, so subcycling is included there, and you can play with that if you wish. As I've said, you might want to control the time step, so you might want to say that the energy doesn't change by any more than a factor of this factor here. And I normally set it to this about 0.1. That seems to be the kind of standard used in literature, especially when using backwards differencing, to keep things roughly stable. At the moment, the code doesn't check this at the beginning of the simulation. Okay. Because as it's written, it would also update the abundances the first time. Okay, so you'd have to then pass dummy abundances to the code the first time, work out the cooling time based on the dE by dt. The code will give you return the dE by the dt that it actually found inside based on the ISM heating and cooling. And then what you could do is the beginning of the simulation, you could then work out what the time steps should be for the very first step. And so you're going the right way to start with. At the moment that's not done, you should maybe put it in if you wish to use it for anything serious, just to be careful. Okay. So just to introduce the subroutines so you can kind of see them if you've been playing around with the Gits repository. If you change to the chemistry branch, you'll find that you have this extra subdirectory called chemcool, which has a bunch of subroutines in it. The top one, the first one, is do chemcool step, is the interface between CERN and the Gauss-Seidel iteration for the chemical reaction networks. Okay, and it controls the subcycling for you. You just pass it a time step dt. It will do what it needs to get through to time step dt, and then return the new abundances, the new energy, and also the rate of the energy change over that time step. The solve chem time step is the one that's actually doing the Gauss-Seidel iteration. You'll see it looks very much like what I just showed you there in terms of its layout. The chemical rate coefficients, because some of them are functions of temperature and density, the code becomes a real mess if you put them in alongside it. So I've put them in a separate module, and so that you can call them separate, and you can go in and see those different reaction rates separately. The only one that's not in there is the cosmic reionization rate, because it is trivially the rate. Okay, there's no functional form there. That just is the rate. So it's the only one that doesn't have an entry in this chemical rate coefficient. So there should only be 7 chemical rate coefficients in that subroutine. There's also a separate subroutine which stores the ISM heating and cooling. So that's got your C+ cooling, your gas dust transfer, and the photoelectric emission, etc. There's also one which will compute the stimulated emission. You have to do this for working out the amount of cooling you have from C+. You have to work out how much of the energy level population that you have is actually being excited by stimulated emission, not by collisions. Okay, so that works that out for you. It's very simple. And there's also in this chemistry constants is where most of the things such as this big L sits, and also the tolerances and things which are you're going to hold steady throughout the simulation. Okay, if you want to find them. So if you can think about it, it is in a sense something like a little bit of a header for the chemistry. It's buried down in that directory. Okay. Okay, it appears in the following subroutines. You have to change, at the moment I've only implemented it in the leapfrog algorithm, the kick, drift, kick. If you wanted to use the moment cutter, you'd have to figure out how to put it in yourself, or if you wanted to use the drift, kick, drift, which we wouldn't recommend anyway, but if you did, you'd have to do that yourself. It's also in this time step size, so once the code's going, it uses that dE by dt, the energy rate, to try and work out a constraint on the time step, so you're not taking too long time steps, which then can then cause problems with the solver. And you also have to change the thermal energy, and so it can work out the pressures and stuff, and it's changed in these files here. Okay, and also the header file has obviously been changed as well. And you'll find it all. Oh, maybe I thought I had a. Okay. But like I said yesterday, if you just grep for chemcool in capital letters, that is the tag that's used in the make file. And so every time, basically all these things are protected by that hash define. Okay, so you can quite quickly find which bits of the code have been changed, which bits haven't. Okay, so what sort of science can you do with that? I mean, it sounds like quite a simple model. It sounds like it might not be useful for science. And in fact, something very, very similar to this, in fact, it might even be even slightly simpler again, where it was used by Claire Dobbs in her galaxy model simulation she was doing with SPH a few years ago. And we were involved, Simon and I were involved in this paper. And she was looking at the amount of H2 that you form in the galaxy and looking at the warm and cold phases of the ISM. And for example, here's the temperature, and she was able to get the cold so the cold regions in the arms and the inter-arm regions are nice and hot and didn't have much H2, and she was able to see how long a GMC would survive going from the inter-arm region where it's formed to where it can get photoassociated in the outside. But again, she was using a very, very simple thing here. At this time, she was using, instead of maybe 6 parsecs, she was using 30 parsecs, and she actually tried changing that number a few times. And the reason why she picked 30 parsecs is that is the distance to the nearest O and B star in the interstellar medium. Okay, so that's where most of your UV photons are going to be coming from. That's going to be dissociating the chemistry, and also it's going to be creating your photoelectric emission. Okay, so that was actually quite a good estimate, quite a good approximation for this type of simulation. So if you wish to do that with it, you can. Okay. Other test cases you can do is just create a turbulent box, start it off with normal ISM densities and run it, and you can start with the H2 and H+ and abundances, probably H2 at 0, I'd imagine, if it's going to be ISM density of about 1. And H+ is set by the balance between cosmic rays and recombinations, and for the normal cosmic reionization rate, you find that the H+ fraction should be around about 10⁻³ in the warm neutral medium. You can maybe use 1 million SPH particles if you wanted to start with, and you probably have to use all 16 cores. You'll find that the first time step is incredibly slow. It has to go away and do the lots and lots of chemistry and cooling, and then it figures out what time steps it's working on, and then it will start to speed up. Okay, but the first time step will be slow, just to warn you. Another one you can do is you can just take two clouds and just slap them together. I think guy at the back was actually thinking about doing this some point during this week. You can take two clouds, put some turbulence into them, and smack them together. Two kind of atomic clouds, which a process that might occur, for example, in the Milky Way or in a starburst galaxy, and you can see how quickly the H2 forms. Okay, so those are things which I can help you set up over the next few days if you wish to do so. I think that's it. I'm done. Thank you.